Chemical Reaction Engineering Laboratory. So last week we have performed an experiment on batch reactor, isothermal batch reactor, where we have demonstrated how to determine the rate constant and verify second order reaction of saponification of ethyl acetate with NaOH. Okay, so in this second week we are going to perform another experiment, which is another ideal batch reactor, which is CSTR, continuous stirred tank reactor. Ready? So this apparatus consists of CSTR, a continuous stirred tank reactor, which is a cylindrical column which has baffles in it, and bottom we have an outlet to collect the samples or discard the final products, and after certain height level we have outlet section. Okay, and we have two inlet sections. One is connected to a peristaltic pump which withdraws the solution from the feed tank A, ethyl NaOH, and we have another pipe tube which is connected to peristaltic pump 2, which is connected to tank B, feed tank B. So in the feed tank B we have ethyl acetate. So you can see the two tanks here. So these two tanks are again a cylindrical vessel with two holes at the bottom. One hole is connected to this level indicator, and another hole is connected to the feed inlet tubes. Okay, so this tube is connected to another outlet there. So this will withdraw the reactant once the pump is switched on. Similarly, another tank. So here also there are two holes. One is for level indicator, another one is for the withdrawal of solution from the tank. Okay, so before starting the experiment we have to ensure that sufficient amount of ethyl acetate and NaOH are present in the system. Okay, we cannot start the reaction with empty tank. Okay, so this cylindrical tank is connected to attached with a stirrer which is run using a motor. Okay, so motor is attached. So this constitutes a simple single CSTR reaction. Actually in the same setup we have 3 CSTRs in series, which we will be performing later.
We demonstrate single CSTR. In that, the aim of the experiment is to study the performance of the CSTR in various flow rates and determine the rate constant.
CSTR, continuous stirred tank reactor. Actually this type of reactor operates continuously in comparison to batch reactor, which is only used for batch reactions, where we feed the reactants into the system and carry out the reaction and withdraw the product. It's a reaction vessel in which the reagents, reactants, and often the solvents are flowing into the reactor, while the products of the reactions are concurrently exiting the vessel. CSTR will consist of a tank reactor, a stirring system to mix the reactant, and we will have two pipelines, one for feed and exit, feed of the reactants and exit of the products. Okay, so CSTRs are not generally used for homogeneous reactions. However, homogeneous reactions are the most convenient ones for the study of CSTR behavior. So that's why we are performing a saponification of ethyl acetate with NaOH in these CSTR studies. Okay. So this stirring apparatus consists of many different designs are available. So we will come to know it in detail in your theory course. And CSTR is one of the few ideal reactors that we will be studying for understanding the reaction mechanisms also. Okay, so some of the ideal assumptions that are made in CSTR are: it assumes the steady state or continuous process. Okay, so we are going to have a steady state condition, so there is continuous flow and continuous output. Okay, so obviously when you switch on a CSTR reactor, we are not going to attain this steady state immediately, so we need some transient time where we attain the steady state. So that's why once we switch on the CSTR, we will wait for the steady state to attain. Okay, so the product analysis we will perform at the steady state only. Okay, so then another assumption made is it is well mixed, or you can say perfectly mixed. So what is the meaning? The mixture in the CSTR is perfectly mixed and it is the same everywhere. The composition is same everywhere in the space in the CSTR. Okay, so how do we maintain that? To maintain these conditions, the fluid into the reactor must be equal to the fluid out of the reactor. That's why we attain the steady state. Okay, and how we get the well mixing condition? To get the perfectly well mixing conditions, we should have a proper agitator impeller blades to rotate. Okay, so thereby we try to maintain a uniform composition throughout. Okay, this animation shows you how if we have two reactants, how they are continuously entering the CSTR tank, and once steady state is attained, how the product is leaving the system. Okay, so that's what we do. Some of the advantages associated with the CSTR are it gives you a very good process control. Okay, so because uniform temperature is maintained because of this assumption that it is perfectly mixed and it is at steady state. Okay, so that way it is simple in designing. Okay, and the labor cost associated with it is also very low. Okay, and if you look at the some of the cons associated with CSTR, the demerits of the CSTR are it cannot be employed for highly viscous fluids. For example, molasses are there, biomass fluids are there, high slurry is there. So in that cases, in CSTR we will not able to get the perfect mixing condition because we need some highly efficient agitator with high horsepower motors to mix the contents if it is highly viscous. Okay, so that's why it is not good for highly viscous fluids. Okay, and another disadvantage with respect to CSTR in comparison to plug flow reactor is the volume of the reactor required for the same conversion is more in comparison to plug flow reactor. So thereby for the same conversion and the same amount of fluids to be processed the volume of the reactor required for CSTR is more than the plug flow reactor. Okay, because we know that from rate equation graphs also, for plug flow reactor it is area under the curve and for CSTR it is rectangle. So obviously for the similar minus 1 by minus RA versus CA, we are going to have different area requirement. Okay, area under the curve is going to be different than area of a rectangle, right? So thereby for CSTR we need more volume of the reactor for same conversion. Okay, and we can write the material balance for the CSTR by writing the general mole balance, where you have accumulation is equal to input minus output plus or minus generation or consumption. So for a steady state operation, we have assumption is means accumulation is 0 and generation of the reactant or consumption of the reactant, all that can be written, and we can get an equation for design equation for CSTR, where you will get the V of the reactor is equal to Na0 minus Na by Ra. Okay.
For batch reactor, NaOH and ethyl acetate, both chemicals are very less quantity I prepared, but CSTR we want large amount, so I prepared bulk 20 liters like that. 0.1 normality ethyl acetate and 0.1 NaOH. And in last lab only we standardization both 0.1 normal HCl and 0.05 NaOH using oxalic acid 0.1 normal. During the reaction we withdraw the samples. In burette we are taking 0.05 NaOH, indicator phenolphthalein indicator, and 6 conical flasks, different fluorides of CSTR.
We are going to perform single CSTR experiment. Okay, so actually it is a setup of 3 CSTRs. So in this we are going to perform a single CSTR reaction. So this setup consists of a cylindrical tank and we have 2 inlet sections, which is through 2 pumps we are going to send in 2 inlets, feed A and feed B, and we have a cylindrical tank and we have an agitator connected to a motor, so which will be rotating. The same is three setup, three experiments are there. So we can do CSTR in series later. So in this laboratory, we are going to perform a single CSTR reaction. So what we have is two inlet and there is a one outlet section. So for inlet, we don't have valve, but there are two pumps. So we can switch on and adjust the speed, the rate of inlet can be adjusted by adjusting the flow rate. Flow rate can be adjusted by adjusting the RPM here. So there are three different RPM we are going to fix. So at three different flow rate speed, we are going to, there will be the rate of inlet will be changed. So then we wait for the outlet also will be, we will have a liquid level, particular level in this CSTR reactor. And after steady state is attained, we wait for 10 to 15 minutes. So after that, what we do is we open this valve and collect 10 ml of sample from the system. Okay. We will be titrating it against 0.05 normal NaOH solution. Same with addition of indicator. And to perform what will be the inlet to this? Again, we are going to study about saponification reaction. So that means that feed A and feed B, we have to fill in the tank. So for that, we are having so we do have two feed tanks, feed tank A and feed tank B. Feed tank, we are going to fill NaOH solution. So already we have shown you this tank. So in this we will be filling at least 10 to 20 liters of NaOH solution in feed A. And similarly here in feed tank B, we will fill with ethyl acetate. Okay, so you know the concentration of ethyl acetate and NaOH being added. So here we can know the level of this liquid in the tank using this thing. So based on the liquid level, you know what is the height in which the liquid is there. If it is getting emptied, we have to again add to the system.
I am taking 20 ml HCl. In conical flask. Two drops phenolphthalein indicator. Murate, you are taking 0.05 NaOH. This one. Stopwatch. In reactor 1, we are taking 10 ml sample for every 10 to 15 minutes after coming the steady state and titrate with 0.05 NaOH.
Okay, before switching on the power input, we have to fill the feed tanks with the reagents. So tank A will be filled with NaOH. So we have already prepared NaOH solution. So we have to fill it. Tank B needs to be filled with ethyl acetate. So we have already prepared ethyl acetate solution. So we have filled the tank. and we should close it. So close the inlet tank. Okay, so now what we have done, we have loaded the inlet tanks with the reactant A and B. Now we are switching on the reactor. Now we will switch on the motor. Okay, we start with 20 rpm now. So what you can see is all the air bubble has to be leaved because we are starting it for the first time after several years. So what this pump does, it's a peristaltic pump which rotates at a very slow flow rate. You can see it can be kept around 10 rpm to 40 rpm. So we can adjust the speed here. So what happens, the flow inlet is going in, so all the air bubbles should escape from it. So that's why we are waiting for 10 to 20 minutes for all the air bubbles to escape from the system. Then we will have continuous flow of the reactants into the system. So it will take some time for the reactants to enter into the tank because all the air bubble has to be escaped. So once we switch on, this stirrer 1 will be rotating. Okay, we are not adjusting that speed. So the motor is making this stirrer to rotate. So it is a CSTR reactor. So what happens? So after certain level, the liquid will be overflowing to the outside. Okay. So with respect to this reaction, we are considering only single CSTR. So that is the product is leaving from the outlet. So product that is formed in the reactor 1. Okay. So what we are going to do, we are waiting for steady state to attain because it is steady state operation. So once the liquid reactants are entering the system, we are going to attain in a CSTR. We know that the concentration will be uniform throughout with respect to time and the position. Okay, so we are waiting for that steady state to be obtained. So meanwhile, we should keep our stopwatch ready, and once we switch on, we should start the stopwatch and we should wait for 10 to 15 minutes to withdraw the sample from it for a given flow rate. After that, we will change the flow rate to another rpm. So then we will wait for steady state to attain. Then again we will open the valve and withdraw the sample. Either you can use a pipette and withdraw the sample, or open this valve to withdraw the sample using a measuring jar. Okay, so before that we already prepared 3 conical flask with 20 ml HCl and 2 drops of indicator. Okay, so we should label it as 1, 2 and 3. So once we are going to do for rpm 1, so that is a sample which we are going to collect after steady state of 20 minutes. So sample 2 and sample 3. So we should not change the thing, that's why better to label it. That is 1, 2 and 3. Okay, so what we will do, after we collect the samples, we will be titrating it against the NaOH solution and note down the endpoint, which is appearance of pale pink color. Okay, now this is the single CSTR reactor. So what we have done, we have kept 2 RPMs, 20 RPM in both the peristatic pumps, which is taking the inlet feed A and feed B from the tank A and tank B, so which are being pumped to the CSTR reactor. So in the CSTR reactor, so we have an agitated stirrer is there. So the stirrer is rotating and we are having 2 inlet reactant A and B entering into the system. So there is an outlet at this point. That means that the level, once it reaches here, that will be going out. Since then we have to start the stopwatch. Okay, so that will be the starting point. So after that we'll wait for 10 to 15 minutes. So we have a steady state attained. So then we will, so time is now 10 minutes, that is almost reaching the steady state. So another 5 minutes we have the steady state being achieved. So then we will open this valve and collect 10 ml of sample from this one and add it to the conical flask where we have 20 ml of HCl and 2 drops of indicator, and it will be titrated against 0.05 normal NaOH. So after that, what we will do, we will empty this CSTR tank, then we will fix another RPM of say 25 or 30 RPM in both the pumps, and we will start the stopwatch once the liquid level reaches up to this height. After that we switch on the stopwatch. So after 10 to 15 minutes, within 10 minutes what we could observe is that liquid level has reached the level up to which we have this outlet section. Okay, so we have an outlet section at this level. So water has reached, the reactants have reached up to this level. Okay, so now we can even observe that there is outlet of water in the exit section. Okay, we can see the water is flowing throughout. Okay, so that means that the tank is filled up to this level. The steady state has been attained. So after 5 to 10 minutes of steady state, we will be withdrawing the sample. Once we are almost now, as we said, it is around 15, going to be 13 minutes. It's 13 minutes now. It's going to be 15 minutes. So after 2 minutes, we will be collecting the sample. We will again open this valve and collect 10 ml of sample and add it to the 20 ml HCl and 2 drops of indicator and titrate it against NaOH solution. So 30 seconds more for 15 minutes. Then start the countdown. 45, 46, 47, 48, 50, 55. So be ready. At the 15th minute, yes, it's 15 minutes. Now we will open the valve and collect 10 ml sample from the bottom of the CSTR and add it to the conical flask number 1. So this is for 1 corresponding to 20 RPM. Now we are going to titrate it against the NaOH. So before that, we will switch off the pump and we have to empty the CSTR tank because we are going to do another RPM. So we have to collect whatever amount is there in the tank and we have to discard it because we cannot use this as a reactant anymore because this is a mixture of product and reacted reactants. So once the tank is empty, close the valve. Okay.
What we have done, 20 ml HCl and 2 drops of phenolphthalein indicator and 10 ml sample. Okay. I am titrating it 0.05 NaOH.
So appearance of permanent pale pink color, if it disappears, we have to add another drop. Yes, I think that's the end point. So we can note down the end point in the burette, okay, and enter it in the tabulation column. So this we have done for 1 RPM. Similarly, we have to do it for another 2 RPMs and withdraw the sample of the steady state is attained. and it is to be titrated against NaOH solution. So thereby we are going to get 3 endpoints value which needs to be entered in the tabulation column. Now, so before starting the switching on the power, we have to ensure that the feed tank is having enough reactant A and B. So whatever is amount left, we are adding NaOH solution to tank A and refill ethyl acetate tank with ethyl acetate 0.1 normality. Okay. So this we are adding for second time. Now the tank is having sufficient amount of NaOH and ethyl acetate. So please close the tank. And what we will do now, we will switch on the motor. So to switch on the motor, we will switch on the power unit first. So once it is switched on, we will switch on. And here we have to switch on this. Once we switch on that, CSTR stirrer is working and both peristaltic pumps are operating. So we will fix the flow rate to 40 rpm. So we are fixing 40 rpm, and what we have to do, we have to wait for the steady state to be obtained, right? So we will start the stopwatch. We'll start the stopwatch and we'll wait for 15 to 20 minutes until the tank is filled and we attain a steady state. So remember, the RPM is low, it is going to take certainly some more time for the tank to be filled up to this outlet level. So once it is filled up to the outlet level, we will wait for another 5 to 10 minutes and we will withdraw the sample from the bottom of the tank. Okay. So how we know that product is filled up to this level? So from the exit section, we will see the liquid is flowing out or not. Okay. So from that we will come to know it is filled. Even if you are shorter, you can climb and see the level in the tank. Okay. You can see the tank is containing some baffles. What is the purpose of baffle? You have learnt in your other courses like mechanical operation and heat transfer courses. We have two inlet sections. And both reactant A and B are pumped by using peristaltic pump, which is used for lower flow rates. Okay. So the speed can be adjusted using this knob. And for this particular second reading, we have kept 40 rpm in tank for feed tank A and for 40 rpm for tank B. Pump A is pumping NaOH solution from tank A, feed tank A, and pump B is pumping ethyl acetate from feed tank B. Okay. So now we have to wait for the steady state to be attained. So it is going to take, but it will take lesser time than the previous value, because last time we had a lower flow rate of 20 rpm. Now we are having 40 rpm. So once it attains, the level is filled up to this level, the product will be leaving from this one. So from then we will wait for another 5 to 10 minutes and collect the sample by opening the valve at the bottom of the tank. In a measuring jar, we will collect 10 ml and again we will go with this one. So we have already completed 1 rpm. So now we will, once we collect, we will pour it in the conical flask number 2. Okay. It's 15 minutes. So what we are going to do, we will collect 10 ml of sample by opening the valve at the bottom of the CSTR, that is continuous sterile tank reactor, and add it to the conical flask number 2, where we have already 20 ml of HCl and 2 drops of phenolphthalein indicator, and we are going to titrate it against NaOH. So before that, you switch off the pump and empty the tank. So we have stopped the stirrer and we are collecting the products formed out. Okay. Now we are stopping the reaction here. So once the tank is empty, we'll close the valve. Okay. Now we are going to titrate it against 0.05 normal NaOH. So already one titration was done. Again refill NaOH solution into the burette using funnel. So once we refill it, we are going to open the valve and start the titration. We should keep shaking the beaker until the permanent pale pink color is attained. So you got the endpoint. Okay, so we are noting down the value. So thus we are completing the second part. So for the we are going to perform a third RPM 60. Okay, so for that again we are going to refill the feed tank. So NaOH is filled in feed tank A again, and ethyl acetate is added into the tank 3. So already we have completed 2 times. This is the third time we are adding. Okay, so close the feed tank and so we have to switch it on. So it's already on. So once we switch on the tank, the stirrer will start rotating. Yes. Now let's switch on this and change the RPM from 40 to 60. So with the 20 RPM difference, we are performing 3 experiments. So start the stopwatch and wait for the steady state to attain. So what is steady state? So after the level of the liquid in the tank rises up to here, we will be able to observe the product leaving the exit stream. Okay. So after that we will wait for 5 to 10 minutes and withdraw 10 ml of sample. We have already completed 2 times and the stopwatch is running. We will wait for 10 to 15 minutes. Often we should check whether any air bubble is entering into this tube or not. Okay. And since the RPM is high, we can expect the liquid level to be filled quickly in the tank. Okay, now it is 15 minutes. We are collecting the sample. So we have to collect 10 ml of sample by opening the valve and collecting it in a measuring jar. So you collect full of this measuring jar, but we will add only 10 ml to the system. So even if you collect little extra, you can throw it out. So we are refilling into the burette. Okay, after filling it up to 0 level, we start the titration. So we are getting the end point and note down the volume of the NaOH consumed and down. Okay. So thereby we are completing the experimental part. Now we will move into the calculation part. Okay, after completing the experiment, so even from the reactant tanks, feed tanks, we have to empty the NaOH and ethyl acetate solution. Okay, so for that we will make use of the valve at the bottom. So using this valve and the valve here, we have to open the valve and collect the NaOH solution. And similarly from feed tank B, we will open this valve, open the valve and collect in ethyl acetate solution. Okay, so thereby we have to keep the tank empty, and if possible you should rinse with water and clean the tank. Okay, so that completes our experimental section. So then there will be calculation part which will be explained.
Dear students, I am Dr. Mridusmita Barwa, and now we are going to talk about the observation and calculation for the experiment. So here, as you can see, this is the observation table. So here we need to consider three flow rates. Okay, so FA is the flow rate of sodium hydroxide, which is reported in liters per hour. FB is the flow rate of ethylene acetate in liters per hour. So then we need to find out V naught. V naught is nothing but summation of FA plus FB in liter per hour. So then we have the titration values. So after that we report the volume of the CSTR. So it is in liter. So it is found out to be 0.97. So once we have the volume of CSTR and then the V naught value, we can find out the space time. So space time tau is given by V by V naught, and this is reported in minute. Okay. So after this we go to the calculation table. So in the calculation table we need to find out Ca, that is the concentration of sodium hydroxide in the exit stream. So it will be reported in gram per mole per liter. Then we have volume V1, which is the volume of HCl in the conical flux, which is taken to be 20 ml. Then we have N1, which is normality of HCl in the conical flux, which is 0.1 normal. Then V3 is the titration value. So we have to consider for the three flow rates. Okay. Then we have N3, which is normality of NaOH taken in the burette. So it is taken to be 0.05 normality. Then V2 is the sample volume added to the conical flux for titration. This has been taken to be 10 ml. So after that we do the calculation. So we find out Ca, which is the concentration of sodium hydroxide in the exit stream in gram mole per liter. Then we find out the rate constant. So the rate constant K will be reported in mole per liter into minute inverse. So then after that we find out the conversion factor XA. So XA will be 1 minus Ca by C naught. So this will be the calculation table. So for these three flow rates, we have the FA, FV value, we have the titer values. So once we have these values, we can find out Ca, Xa and K. Okay. So we are going to get three values of K. So once we find out this K, which is the rate constant, we have to find out the average of these values and then report it. So in the resultant inference, we have to report the value of K. So average it out, okay, in this unit and then report it, okay, and we have to conclude, okay. So that's how we have to express the observation and calculation table.
Here we have the values for practicing the calculations. Write your results and inference and submit your file to us.
So we can summarize that in this experiment we have demonstrated an ideal reactor, which is CSTR, continuous stirred tank reactor. In this we have determined the reaction rate constant at ambient temperature for the saponification of ethyl acetate reaction. We have studied the performance of CSTR in terms of conversion of reactants with respect to varying reactor volume and feed flow rate. So thank you so much, dear students, for joining Lion Rajmohan sir's classroom. Bye.
We sincerely acknowledge the contributions of Dr. Vidyasagar, Dr. Manogar, and Dr. Ramya for the infrastructure development in this CRE laboratory, and we also thank our previous HODs, Professor Sarath Babu, Professor Sirishwanavani, and our current HOD, our dear Dr. Srinath.